Okay, today we're going to talk about alternating series, and that an alternating series is just exactly what it sounds like, is that its terms alternate between positive and negative. So here are two examples of series that alternate. 1 minus 1/2 plus 1/3 minus 1/4. You can see that the signs alternate positive and negative. And the way that you determine if a series is alternating is that you're going to see -1 either to the n plus 1 power or -1 to the n power. And the only difference between those two is whether or not the series starts with a positive or a negative number, depending upon what your n is. So anytime you see that -1 to either the n or the n plus 1 power, you know that the terms are going to be alternating. Okay, so we're going to determine whether or not alternating series will converge or diverge. So in general, just knowing that the limit as n approaches infinity of a sub n equals 0 doesn't tell us very much about the convergence of a series. We know that if that limit does not equal 0, then the series will diverge by the nth term test. But if it equals 0, we were kind of at a loss and we had to use some other different kind of test to determine if the series converged or diverges. However, it turns out that for an alternating series must converge if the terms have a limit of 0 and the terms decrease in magnitude. And that just means that the terms are getting smaller. So the formal definition is as follows. So if you have an alternating series in the form of -1 to the n times a to the n or -1 to the n plus 1 times a to the n, then it will converge if the following two conditions are met. And a sub n plus 1 less than or equal to a sub n just means that your terms are decreasing. And then here we have the limit as n approaches infinity of a sub n equals 0. Okay, let me back up for just a minute though. The a sub n part is the part that's everything about the series that's not attached to the -1 to the n. So the -1 to the n is kind of separate, and when we talk about a sub n, it's all the rest of it. So like for this first example up here, the a sub n part is the 1 over n. And for the second example, the a sub n part is the 1 over n factorial. So just when we talk about the a sub n part, we're just talking about the part that doesn't have the -1 to the n on it. The -1 to the n or -1 to the n plus 1 just tells us that the series is alternating. Okay, so the big thing here, and I've just kind of summarized it. In other words, a series will converge if its terms are alternating in sign, decrease in magnitude, and have a limit of 0. So those are the three things you need to look for. And you should recognize first if a series is alternating in signs, and then if the terms are decreasing in magnitude and have a limit of 0, then it will converge. This is one of the easier tests that we're going to deal with. Okay, now I do need to point out that the alternating series test does not say that if your limit as n approaches infinity of a sub n does not equal 0, then the series diverges by the alternating series test. The alternating series test can only be used to prove convergence. It's kind of like the nth term test can only be used to prove divergence. So if the limit as n approaches infinity of a sub n does not equal 0, then the series actually diverges by the nth term test, not by the alternating series test. So you will never ever say the series diverges by the alternating series test. If it's an alternating series and the limit as n approaches infinity does not equal 0, then you say that it diverges by the nth term test. Okay, so let's determine whether the following series converge or diverge. All right, so we do see that it's alternating. So when you see that you have an alternating series, the very first thing that I want you to do is I want you to find the limit as n approaches infinity. So limit as n approaches infinity. And remember, you just take the limit as n approaches infinity of the a sub n part, not the alternating part. So that's just 1 over n squared. And that limit as n approaches infinity does equal 0. And we know that our terms are alternating because of the -1 to the n. We know that they are decreasing because if you just kind of plug a few numbers in your head, if you plug in 1 for n, you're going to get 1 over 1 squared. If you plug in a 2 for n, you're going to get 1 over 2 squared, or 1/4. 3 for n is going to give you 1/9, so those terms are decreasing, and the limit as n approaches infinity equals 0. So we say that because the terms are alternating, decreasing in magnitude, and have a limit of 0, the series converges. And I apologize, but for the alternating series test, I want you to write out those 3 things. The terms are alternating, decreasing in magnitude, and have a limit of 0, and therefore it converges. So I apologize that you have to write all that out, but that's what I want you to do. Okay, let's look at number 2. Again, we see that it's alternating because of the -1 to the n plus 1. So the first thing we want to do is find the limit as n approaches infinity of the a sub n part. Well, the a sub n part is n over 2n minus 1. And because we're taking a limit as n approaches infinity, and the degree of the top and the degree of the bottom are the same, we can play the coefficient game. So the ratio of leading coefficients is 1/2. So our limit as n approaches infinity equals 1/2. So what that means is that the terms are approaching 1/2, so eventually you're going to continue adding up 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2 forever and ever and ever. So therefore, this series diverges. But because the nth term does not approach 0, this series diverges by the nth term test. All right, it's pretty straightforward. For a convergent alternating series, a partial sum f sub n can be a useful approximation for the sum s of the series. So some of these types of series, we're going to talk about how close of an approximation we can get when we just add up a few terms. And the alternating series is one of those that we're going to talk about. So if a series has terms that are alternating, decreasing in magnitude, and have a limit of 0, so there's your 3 things again that we're always going to talk about with alternating series, then the series converges so that it has a sum of s. So this sum s would be the sum if you added up every single term, the infinite number of terms that you add up. Now, that value of s is going to be very difficult, if not impossible, to find for most series. Okay, so because we can't always find the exact sum of those infinite terms, a lot of times what we will do is make an approximation using a few terms, and that's what a partial sum is. The partial sum s sub n is the sum of the first n terms. If I wanted to find s sub 4, then I would be finding the sum of the first 4 terms. All right, so let me kind of explain this formula and then we'll talk about it a little bit more. Okay, so S is the actual sum. If we were to add up every single term, an infinite number of terms. And remember that that is impossible or extremely hard to find. Okay, so S sub n is the sum of the first n terms. Okay, R of n is called the remainder or the error. If you take the actual sum and subtract your approximation using the first n terms, then you get your remainder or your error. And what this is saying is that your error is always going to be less than or equal to a sub n plus 1. So that's the term, that's the n plus 1 term. So if you used n terms in your approximation, then your error is going to be less than the next term. You can think of it as the first term not used in the approximation. So in other words, if your three conditions are met, meaning your terms are alternating, decreasing in magnitude, and have a limit of 0, then you can approximate the sum of an alternating series by using the nth partial sum, S sub n, and your error will be less than or equal to the absolute value of the first neglected term. So basically your error is less than the next term. And this looks really, really complicated, but I promise that it's not. It's super, super easy. All right, so let me show you. All right, so number 3, find the error associated with using S sub 5 to approximate the sum from n equals 1 to infinity of negative 1 to the n over 2 to the n plus 1. All right, so we know that it's alternating because of the negative 1 to the n. We do need to make sure that it's a convergent alternating series because that's the only way that you can use this error is if it's a convergent alternating series. So let's kind of go through it. So our terms are alternating. If you think about your a sub n, and you don't always have to write this down, but the a sub n part, remember, is the part that's not the negative 1 to the n. So we have 1 over 2 to the n plus 1. So as n gets bigger and bigger and bigger, your terms are going to be decreasing. You're going to get 1/4, 1/9, 1/16, etc. And if you take the limit as n approaches infinity of a sub n, then you are going to get 0. So you can just say, because your terms are alternating, decreasing in magnitude, and have a limit of 0, then the actual sum minus S sub 5 will be less than the first neglected term. So if we use the first 5 terms to make our approximation, then the first neglected term is that 6th term. So it's going to be less than a sub 6. And I want you to get in the habit of using this notation right here. Your error is the difference of the full sum that we're unable to find because it's an infinite series minus whatever your approximation is. In this case, they told us that we were going to use S sub 5, the first 5 terms. So your error is less than the first neglected term. So I want you to get in the habit of writing that on your paper. So essentially, then we can say that the error is going to be less than, and actually all of this is absolute value because error is just basically a quantity that you can go in either direction of your estimate and still be within the range of the actual sum. So our error is going to be less than the absolute value of the 6th term. So if I plug a 6 in for n, and I will get 2 to the 7th. And 2 to the 7th is approximately 0.007813. So what that means is that if I use the first 5 terms of that series to approximate that infinite series, then my error in using that approximation is going to be smaller than 0.007813. So whatever my approximation is, the actual sum might be 0.077813 bigger than that, or 0.007813 smaller than my approximation. And we'll talk a little bit more about that bound for the error in just a minute. All right, number 4, what is the least number of terms you could use to find an approximation of the sum from n equals 1 to infinity of -1 to the n plus 1 over n squared with an error less than 1 over 1/50th? Explain your answer. Okay, so again, we have an alternating series, so we need to make sure that it's a convergent alternating series, or at least communicate to our reader that we recognize that it's a convergent alternating series. So because the terms alternate, decrease in magnitude, and have a limit of 0, we know that our error, which is denoted as the actual sum s minus s sub n, has to be less than the first neglected term, and we denote that as a sub n plus 1. So on this problem, we have to think kind of backwards a little bit. The a sub n is 1 over n squared. So we need to think what value of n would give us a number that's just a little bit smaller than 1 over 1/50th. And I think when I work this through, you'll see it. But if n is 13, if our first neglected term is the 13th term, then the 13th term is going to be 1 over 169, and that's less than 1 1/50th. So the answer is 12 terms, because s minus s sub 12 will be less than the 13th term, which would be 1 over 13 squared, which is 1 over 169, which is less than 1 over 1/50th. So you just have to kind of think backwards on that problem. Okay, last example. So we've got the series n equals 1 to infinity of -1 to the n plus 1 over n factorial. Part A, approximate the sum s of the series by using its first 4 terms. Okay, so remember s is the full sum, the sum of the infinite series, all the terms. All right, so we're going to approximate that sum by using the sum of the first 4 terms. And the sum of the first 4 terms is going to be plug in a 1, plug in a 2, plug in a 3, plug in a 4, and add them all together. So if I plug in a 1 for n, I'm going to get positive 1 over 1 factorial, so that's 1. If I plug in a 2 for n, I'm going to get negative 1 over 2 factorial. If I plug in a 3 for n, I am going to get positive 1 over 3 factorial. And if I plug in a 4 for n, I'm going to get negative 1 over 4 factorial. And if you type that into your calculator, you would get 0.625. Okay, and that's all that part A is asking us to do, is just use the first 4 terms to estimate that. All right, B, explain why the estimate found in part A differs from the actual value by less than 1 over 100. All right, so because we're talking about error here, we've got to prove that we can use the alternating series error. So we have to prove that this is a convergent alternating series. So you do have to write because the terms are alternating, decreasing in magnitude, and have a limit of 0, then our error, which is denoted as s minus s sub 4, will be less than the first neglected term. So if I use the first 4 terms in my approximation, then my first neglected term that I did not use would be the fifth term. So my error is going to be less than the fifth term, and the fifth term is 1 over 5 factorial. And it will be in your best interest to have your factorials probably through 5, maybe 6 memorized, but 1 over 5 factorial is 1/120th. So our error is less than 1/120th, which is less than 1/100th. And that's really what I would expect you to write. You've got to write out, because the terms are alternating, decreasing in magnitude, and have a limit of 0, then our notation for error, which is s minus s sub 4 in this case, is going to be less than your first neglected term, which is a sub 5 in this case. And then you can go on to kind of use more just general language of your error is going to be less than 1 over 5 factorial. And remember that that first neglected term is really also, it's the absolute value of that first neglected term. I don't think you necessarily have to write that, but error is always positive. All right, and then part C is explain why S cannot equal 0.7. Okay, this is kind of an interesting problem, and it's not difficult as long as you understand what they're trying to ask. So remember that S is the total sum. It's this infinite sum. So they're saying, why can S not equal 0.7? Well, it all goes back to the fact that if you use an approximation, or if you approximate S by using a partial sum, then your error is bounded by the absolute value of that first neglected term. And what I mean by bounded by the absolute value of that first neglected term is that whatever your approximation was, so like in this case, it was the 0.625. Well, if our error is less than 1/20th, then that means, 1/120th, then that means that if I take my approximation and add 1/120th, or if I take my approximation and I subtract 1/120th, that the actual sum of that series is going to fall between those two numbers. So whatever your approximation is, what the bound on your error means is that you can go that distance to the left or to the right of your approximation. So our approximation is 0.625. We can go 1/120th greater than that, or 1/120th less than that, and that's basically the range of values that that actual sum will fall into. So if I actually put these values into my calculator, 0.625 minus 1/120th is 0.617, and 0.625 plus 1/120th is 0.633. So what I've shown here is that the actual sum of this infinite series is going to fall somewhere between 0.617 and 0.633. And therefore, there's no way that the actual sum could equal 0.7, because 0.7 is out of that range that's bounded by our approximation and our error. So that's kind of the way I think about it. If you really want a specific formula for that, then your sum, actual sum, is going to fall between the partial sum using n terms plus that next term. That would be the upper bound. And then the lower bound would be the sum of the first n terms minus your error or that first neglected term. But I would rather you just kind of think about it in terms of take your approximation and add and subtract that error to get that range of values. All right, that's it for alternating series. See you tomorrow.